In the next two videos, we are going to create a camera system. In the first part, we are going to implement the so-called mouse look script. And at the end of the video, we will be able to look around the scene. I'm going to show you like this. So with the mouse, now I can look around this scene. So as you can see, if I move left, it looks left, and right, up and down. So this what we are going to implement in this video. And in the next video we are going to implement the WASD keyboard movement. So we will be able to actually walk around the scene. So I'm just created this simple scene where we have this floor with this floor texture, this rotating textured cube, and also this monkey head from Blender, also textured. So let's get started. Before I continue, I just wanted to let you know that this two-part video tutorials will be based completely on the learnopengl.com. If you go to Getting Started Camera, so it will be based on this written tutorial. And I'm also going to add this link to the video description. So I just resetted the scene, so now we have just a static scene with this floor, the monkey head and this rotating cube. And now let's start to actually implement the camera. I already created this camera.py, which is now empty. And the first thing we need to do is actually import the necessary modules from peer and also from the math module. And from the peer we are going to use the vector free and also the vector free with the lowercase v and the matrix 44 modules. So let's import those. The next thing we need to import is from the math module, which is the part of the standard Python library, the sine, cosine and the radians function. Okay, so these are all the necessary imports, and I'm going to create a camera class. Okay, so now the camera is ready, although I'm going to name it camera with an uppercase C. We need to create 4 vectors. One is the camera's position, which will be a vector free, the camera front, so this will be the direction where the camera looks at. We are going to define the camera up and the camera right vectors. Okay, these are all the camera vectors we need to actually create this camera system. And we are going to create 3 more member variables to this camera class, which will be the mouse sensitivity, which will be just a scalar, this jaw and also the pitch. Okay, now we are ready. These are all the member variables which we need. And now I'm going to define 3 methods. One will be the getViewMatrix, the second will be the process mouse movement, and the third will be the update the camera vectors. The process mouse movement will take actually 3 arguments next to self. So one will be the x offset, the second will be the y offset, and the third argument will be the constraint pitch, which will be a boolean, and it will be by default set to true. The first method I am going to actually finish is the get view matrix, which is the simplest from these 3. And the get view matrix will just return from peer the create look at function. So we are going to use this create look at. In my previous older OpenGL and camera system video, that time peer didn't had this create look at function. So if you go to my GitHub page to OpenGL Season 2, which was recorded more than 2 years ago, here is the camera. I'm also going to add this link to the video description. Here I had to create the look at function because, as I said, peer at the time didn't had this look at function. And I created this look at function based on from this tutorial. If you scroll down, you will find the source code to here replace GLM's look at function with your own implementation. See if it still acts the same. If you click on the solution, you will find this written in C++, and in my version it is converted to Python. So okay, now let's go to the camera class and just return the create look at function. Okay, this method is just this simple. It returns the from peers matrix 44 the create look at function, with the first argument is the camera position, and the next argument is the target. So this is the eye position, this is the target, so which is the eye position plus the front vector, and of course the last argument is the camera's up vector. And now let's define this process mouse movement, or just finish this process mouse movement function. Okay, so this is the process mouse movement, and let's talk a little bit about this method. So first thing we are calculating is the x offset times, which will be times equals the x offset times the mouse sensitivity. And also the y offset will be the y offset times the mouse sensitivity. And also calculating the self.jaw and the self.pitch. And what is the jaw and what is the pitch? If you go here to learn OpenGL and just scroll a little bit up, so here are the pitch, jaw, and the roll. So the pitch makes move the camera or the head of the, if it is a character, up and down. So as you can see on the x-axis, the jaw moves to the left or the right on the y-axis, so it turns the head. And the roll rolls the head or the camera on the z-axis. And I'm also created something here in Blender. So technically when you move, here is the x-axis. When you rotate on x-axis, this is the pitch. And also if you rotate on in Blender, the z-axis is actually up-down. In OpenGL, the y-axis is up-down. So if you rotate it on the up-down axis, it turns left or right. So this is the jaw. And if you rotate it in Blender, if you rotate it on the y-axis, but don't forget, the y-axis is actually the z-axis in OpenGL, it just rolls the camera like this. And if you go back to the code, so we are adding to the jaw the x offset and to the pitch the y offset. And here we are constraining the pitch. So if the pitch is bigger than 45 degrees, we are going to set it to 45. If the pitch is less than negative 45 degrees, we are going to set it to negative 45. In this way, we can prevent the following. So if I'm going to rotate this camera on the pitch, now, because this is constrained, we can look 45 degrees up. And here it is constrained, so we cannot do this. We cannot rotate our head or our camera 90 or 360 degrees. So we are constraining it just 45 up and negative 45 down, like a real head. And lastly, we just calling the self.update camera vectors. What I'm going to write out next. So okay, so now we just created a local vector 3, and we are calculating with some trigonometry, so cosine and sine functions. We are calculating the front x with cosine of radians of the jaw times the cosine of radians the pitch. The front y is the sine of radians of the pitch, and the front z is the sine of radians of jaw times the cosine of radians of the pitch. And as I said, if you want to know more about these, just go to here in the camera section, and here is the look around and the Euler angles. It is explained much better than I can. So let's continue this with setting the camera front vector, the camera right vector, and the camera up vector. Okay, so all the functionality is ready for the camera class, at least for the mouse movement. So in the update camera vectors, I'm just calculated the self.camera front based on this local front vector. So, and I also normalized it. So you can use vector dot normalize with an S, and here if you want to use it, as you can see, here is also with normalize with Z. I'm going to leave it as normalize. Maybe it will be deleted later, I don't know, because I think the correct way is actually with the Z, normalize. So we are normalizing the front vector, and of course we are setting the self.camera front to this normalized front vector. The camera right is calculated. Also, it is a normalized vector of the cross product of the camera's front, and here is the up vector. And the camera's up, you can also just set it like here. When I created the first OpenGL series, and when I implemented the camera, I used here the self.camera up, and it worked, but it wasn't perfect because unwanted rolling were actually at the time in my camera. So later I just updated the code. I also created a video about that 2 or 3 years ago, and I'm just, instead of adding here the cameras up, I'm just added here, created here always just a new vector which points up. So I'm going to change it back to vector 3 x0 y1 z0, and the camera up will be also the normalized vector of the vector 3 that cross product of camera's right and the camera's front. So here is everything for now. It is everything finished. I'm going back to the main file, so the episode 16 camera, and I'm going to just import this camera and also create a callback function for registering, for GLFW, for registering the actual mouse movement. So the next step will be to actually import the camera to the main module, which is this one, with the window and scene. Okay, so first import the camera from the camera module, then create a camera instance, calculating I'm going to create 2 variables, the window's width and the window's height. And we are going to create 2 other variables, which will be last x and the last y, which will be just the window's width divided by 2, and the last y will be the window's height divided by 2. And also I'm going to create a first mouse, which will be a boolean, and by default it will be set to true. Okay, so the next step will be actually define 2 functions, 2 callback functions. But before I continue, I'm just going to change everything to this width and height. So when I'm creating here the GLFW window, it will be now set to width, and this will be set to height. And let me see if I'm using 1280 and 720. Here I'm also using 1280, so I'm just going to change it to width divided by the height, which is 720. And of course, when we change the window's width, here is the callback function for it. The new width and the new height is automatically calculated by this callback function, and the projection matrix is recalculated. let's start to define those two callback functions. One will be the mouse look callback, and the second will be the mouse enter callback. So okay, so in the mouse look callback, this function will be called every time I'm moving the mouse inside the GLFW window. And the first thing we are going to use is the last x and the last y global variables. And we are also going to create an if condition. If the mouse first enters the window, it will be the last x and the last y will be reset to this x position and y position, which is automatically set by the GLFW. Okay, the mouse look callback is ready. So first we are going to use here the last x and the last y, which is by default set to Windows width divided by 2, and the last y is the Windows height divided by 2. So when the mouse first enters the screen, the window, the last x will be set to x position and the last y will be set to y position. And as I said, the x and the y position will be automatically set to these two arguments by GLFW. Then I'm creating two locales, which is the x offset and the y offset, and the x offset is just the x position minus the last x, and the y offset is the last y minus the y position. This is inverted because remember that in OpenGL the y-axis goes from bottom to top, so it increases from bottom to top, and in the mouse coordinates starts from top to bottom, so that's why we need to invert these. And then the last x will be set to x position and the last y will be set to y position. And the last line in this mouse look callback is the camera.process mouse movement with the x offset and the y offset, which we'll call the camera's process mouse movement method with all of these. Of course, which just calls the self.update camera vectors, which will update the camera vectors. And now let's do the second callback function, which is the mouse enter callback. So the mouse enter callback is just this simple. Every time when we I'm just going to show you. So every time when the mouse enters the window, this mouse enter callback will be called, and if entered, then first mouse will be set to false. And when the mouse leaves the window, this callback will be called, and because it is leaving, now this else will be fired and the first mouse will be set to true. So, and the first mouse is used here in the mouse look callback, so every time when we entering the mouse, the window with the mouse, this last x and last y will be set to x position and y position. So if we leave the window, now this first mouse is set to true, so if we go back to the window, this calculation will always just the last x and the last y will be always set to x position and y position. Okay, now, it's time to register these two callback functions with glfw, and we are almost ready. So here, after this Windows set size callback, I'm going to register these two callbacks. So with these two lines, the mouse look callback is registered with glfw, and the mouse enter callback is also registered with glfw. So the very last thing to actually make it work is just in the main application loop, just always recalculate the view matrix. So here I'm set at this view matrix, which is just a static view. I'm just going to comment this out, and also this GL uniform matrix, which sets the view. And now it will be, in every frame, the view will be recalculated, so it will need to go to the main application loop. Okay, technically the code is ready, so it's time to actually try it out. Fingers crossed. Okay, now we have here an error, which true divide, so possibly we have in the camera somewhere. Okay, so the problem came from that we used vector free with integers. So I'm just converted everything to float, so 0.0, 4.0, 3.0. So everywhere where I'm creating vector free, you need to give it floats, not integers, so not whole numbers. So as you can see, 0.0, 1.0, 0.0 here also, and here in the update camera vectors also just floats, and here when we calculating the camera's right, here also floats, use just floats, not integers. And now, as you can see, the camera actually works. So if I move down, up, left and right, so the pitch is constrained, so if I move down, as you can see, here is the negative 45 degree, I cannot move the camera, rotate the camera's jaw, or not the jaw, but the pitch. It cannot be less than negative 45, and also it applies to positive 45, so it cannot be bigger than 45 degrees. Okay, so it was a long video. In the next video I'm just going to implement the WASD movement.